Hi, welcome to this lesson on hypothesis and significance. In the previous lessons, you learned about the sampling methods available to collect your data, and you learned about probability. With this in mind, it's now time to put your collected data to work. We've briefly talked about comparing groups in the previous lessons, but how do you actually go about testing this? Today, you will start to work with hypotheses and significant levels. This will allow us to go from describing data, much like what we did in Module 1, to making statistical conclusions about the population. That's going to be the topic of this lesson. Let's get started. Let's start with hypotheses. I know that you probably have an idea of what you think a hypothesis is. If you've taken any science class in college, you have an understanding of what a hypothesis is. But in statistics, there's a very specific thing that we're talking about when we say hypothesis. A statistical hypothesis is an assumption about a population parameter. A parameter is a measurable characteristic of a population, such as a mean or a standard deviation. This assumption on the population parameter may or may not be true. For instance, you have this suspicion that due to recent management change, people work longer hours than before. Whereas before people worked for 8.5 hours, you now believe that they work for longer than that. To test our hypothesis, we use both a null hypothesis and an alternative hypothesis. Let's start with the null hypothesis. The null in the null hypothesis stands for 0, and in statistics, we use it as the default hypothesis. In statistics, we denote the null hypothesis as HO or H0. This hypothesis states that the sample observations result purely from chance, or in other words, that our current known value of the parameter is the correct value. For instance, our null hypothesis would be that people work for 8.5 hours a day. But that's not what we're actually interested in. We're interested in something that's called the alternative hypothesis. The alternative hypothesis, denoted by H1 or HA, is the hypothesis that sample observations are influenced by some non-random variable. This is the hypothesis that we're actually testing. In our example, this would be that people work on average longer than 8.5 hours a day. However, we test this hypothesis by rejecting the null hypothesis, rather than accepting the alternative hypothesis. Now you may wonder why we do that, and we do this due to something called falsification. This concept was popularized by the famous philosopher of science Karl Popper. He proposed that science can never verify hypotheses, only falsify them. And by falsifying the hypothesis, we get closer to the actual truth. The famous example is that of black and white swans. Until the end of the 17th century, Europeans had held a strong conviction that all swans were white. They had seen them in the local village pond and in the village close by. As they explored further afield, they still only found white swans. Thus, the theory was that all swans were white, or in statistical terms, H0, all swans are white. However, the first reported sighting of a black swan by the Dutch explorer Willem de Vlaming in 1697 undermined this notion that all swans are white. No matter how many white swans had previously been seen, that one single black swan undermined the thousands of white swans they had seen previously. At that point, the world knew that not all swans were white, hence rejecting the null hypothesis that all swans are white. This type of falsification is standard in statistics and is of paramount importance for statistical research. We never accept something to be true, even the alternative hypothesis, as it's impossible to completely accept something as true. Try and prove that the sun is real, for instance. We can see it, sure, but it could be a very elaborate movie prop for all you know. It's very hard to prove something to be definitively true. But we can much easier, however, claim that something is not true. You could see thousands of white swans, but that one black swan was all that was needed to disprove the hypothesis that all swans are white. So now you understand why we try to reject the null hypothesis. But how do you actually test this? Let's go back to our example of wanting to test whether people work for longer hours than before. The null hypothesis in this situation is that people do still work for 8.5 hours a day. Or in statistical terms, H0 equals 8.5. The alternative hypothesis is that employees do, in fact, work for longer hours, or in statistical terms, H1 is larger than 8.5. The null hypothesis and alternative hypothesis are what we call mathematical opposites. Both cannot be true at the same time. Due to the falsification I mentioned earlier, we have two possible outcomes to this test. We either reject the null hypothesis or we fail to reject the null hypothesis. Now, when you reject the null hypothesis, you are stating that the alternative hypothesis has more truth to it than the null hypothesis. You don't accept the alternative hypothesis because, as I said earlier, you can never fully accept a scientific hypothesis, but you can reject a hypothesis, which is what we're doing in this case. If we fail to reject the null hypothesis, that means that we think the null hypothesis has more truth to it and will remain as is. Now, you collect your data and see that the average working hours is indeed higher than 8.5. In fact, it's 9.5 hours right now, which is a pretty significant jump from 8.5 hours. Does that mean you reject the null hypothesis? Not necessarily, as this difference in mean could be due to random chance. It could be that you simply selected the sample which is accidentally working more hours. What you want to know is whether or not this difference is statistically significant or not. Or in other words, whether it's unlikely that this difference between the sample and the population is due to chance. To test this, we can use a variety of statistical tests, such as the t-test, ANOVA, and more. We'll cover all of these in modules 3 and 4. For now, I want to skip to the conclusion and talk about the end result. In statistics, we don't want to do something on a whim. We have to have a concrete way of looking at our null hypothesis and have a method in place to decide when we should reject our null hypothesis. For this, we use alpha levels and p-values. The alpha level, also called the significance level, concerns the probability of rejecting the null hypothesis when the null hypothesis is true. This is also called a type 1 error. It is similar to the false positive I spoke about in a previous lesson. In simpler terms, it's the probability to falsely infer the existence of something that is not there. Most people use an alpha of 0.05, which means that there is a 5% probability of rejecting the null hypothesis, even though it is true. However, this number is subjective, and you may want to have a higher or lower alpha level depending on the test that you're doing. Once you've chosen your alpha level, you're ready to conduct your hypothesis test. After you've done your hypothesis test, for instance a t-test, you will receive a p-value. The p-value is a measure of the strength of the evidence against the null hypothesis. This means that the p-value is the probability of getting the observed value of the test statistic if the null hypothesis is actually true. This means that the larger the p-value is, the larger the probability that the null hypothesis is true. And the smaller the p-value, the smaller the probability that the null hypothesis is true. Now on your screen, you will see a number of p-values. If your p-value is smaller than 0.05, there is strong evidence against the null hypothesis. If your p-value is between 0.05 and 0.1, there is some weak evidence against the null hypothesis. If your p-value is larger than 0.1, there is little or no evidence against the null hypothesis. If your p-value is lower than your predetermined alpha level, or in other words, it is statistically significant, you can reject the null hypothesis, meaning that there's a higher chance that your alternative hypothesis is closer to the truth than the null hypothesis. Of course, we want to reduce the role of luck as much as we can, so we have to set a cutoff point. This cutoff point, or the alpha, is usually put at 5% in the social sciences. So if the p-value is equal or below 0.05, then the null hypothesis is rejected. However, your cutoff point also changes depending on whether you perform your statistical test one- or two-tailed. You're using a one-tailed test when you think your sample parameter differs from the null hypothesis parameter in one direction, so either larger or smaller. So HA is larger than HO, or HA is smaller than HO. For example, based on literature, you expect that stores with higher levels of engagement have a higher annual revenue. You can use a one-tailed test here, as this has been shown to be the case, so you're quite confident about the directionality. You're using a two-tailed test if you think this direction could go either way, so you don't know whether this direction is either smaller or larger. This means your HA becomes HA is not HO. I will explain in a bit more detail, starting with the two-tailed test. If you're using a significance level of 0.05, a two-tailed test allots half of your alpha to test the statistical significance in one direction, and half of your alpha to testing statistical significance in the other direction. This means that 0.025 is in each tail of the distribution of your test statistic. For example, we may wish to compare the mean of a sample to a given value x using a t-test. Our null hypothesis is that the mean is equal to x. A two-tailed test will test both if the mean is significantly greater than x and if the mean is significantly less than x. The mean is considered significantly different from x if the test statistic is in the top 2.5% or bottom 2.5% of its probability distribution, which means that your cutoff point becomes 0.025. A one-tailed test, for example the impact of engagement on store revenue, puts all of your alpha to test the statistical significance in one direction. This means that 0.05 is in one tail of the distribution of your test statistic. When using a one-tailed test, you are testing for the possibility of the relationship in one direction and completely disregarding the possibility of a relationship in the other direction. In this case, you assume that higher engagement will never lead to lower revenue. Keep this in mind when designing your alternative hypothesis, as having a one-tailed test means your p-value can be larger than with a two-tailed test. This will have an effect on your alpha, or when your test statistic becomes statistically significant. If your p-value is higher than your alpha level, you will fail to reject the null hypothesis. This can lead to a type 2 error, where you fail to reject a null hypothesis even when it's false. Both type 1 and type 2 errors depend on your alpha level. When you want to decrease the likelihood of rejecting the null hypothesis when the null hypothesis is true, you have to decrease your alpha level to a lower standard. However, this also means that there is a higher chance for a type 2 error, where you fail to reject a false null hypothesis as your alpha level is now lower than before. That's it for this lesson. To sum up, in this lesson we spoke about the null and alternative hypothesis, falsification and its place in statistics, and we spoke about significance levels and p-values. See you all in the next lesson.